All right, so continuation of curve sketching video from where we started in class. And so we're going to be on example 4, starting with this video. And so we're going to connect a function, its derivative, and its second derivative. Okay, so we're going to look at this graph. So this graph that we're looking at is at the moment, okay, so the first thing we're going to look at is we're going to suppose that this graph is y equals f of x. So this is the f of x function. On what open intervals is f of x both increasing and concave up? So looking at this graph, it is increasing and concave up from here to here. And then again, so from -5 to -2, and then again from 4 to 6. There's where you have increasing and concave up. So it is -5 to -2 union 4 to 6. Those are our intervals if this is f of x, okay? So again, on what intervals is f of x both decreasing and concave down? So decreasing and concave down would only be from -1 to 2. That's the only place that I'm decreasing and I'm concave down. Because there's other places it's decreasing, but they're concave up in those places. So this would be from -1 to 2. And at what x values does f have an inflection point? So inflection points would be where we change from concave up to concave down. So right here, or we change from concave down to concave up, so right here, and then again concave up to concave down. So those points would be our points of inflection. So that'd be -2, 2, and 6. Okay, now the interesting next question is, let's say that instead, now let's consider that graph to be the graph of f prime. So now the question is, on what open intervals is f of x decreasing? Now remember, this time you're thinking of this graph as f prime. Okay, so I'm going to get rid of those marks. So now we're considering this to be the derivative, and we want to know when is f of x decreasing. Well, f of x would be decreasing anytime its derivative is below the x-axis. So that would be from 2 to 6. So f of x is decreasing on 2 to 6, and that's because f prime of x is less than 0, because the graph again now is considered to be f prime. So at what values does f of x have a local maximum? Again, a local maximum where this graph that we're looking at is the derivative. So you're going to have a maximum if you have the derivative change from positive to negative, because that means right here you have positive, okay, and then it changes to negative, which means that this point right there must be a local maximum. Because if this graph is the derivative, if this is f prime changes from positive to negative only at that place, so that's where we have a local maximum. So we will have local max at x equals 2, because f prime of x, which is the graph now, is called f prime, changes from positive to negative. Okay? And then it asks, on what open intervals is the graph concave down? Okay, so again, this graph is f prime. So if I want to know when is f concave down, it's going to be concave down anywhere f prime is decreasing. So it is decreasing here, decreasing here. So those would be the places that f would be concave down. So negative infinity to negative 5, negative 1 to 4. Oops. Went the wrong way. So negative 8 to negative 5, union negative 1 to 4, because f prime of x is decreasing. Okay, so if f prime is decreasing, f is concave down. And then it says at what value or values does f of x have an inflection point? So an inflection point would be where your concavity changes. Well, your concavity is going to change if your function changes from decreasing, if f prime changes from decreasing to increasing, or increasing to decreasing, or if you say about where your f double prime signs are. I would just stick with the decreasing to increasing and so on. So basically you're going to have an inflection point here because f prime changes from decreasing to increasing. So that means it's going to go from concave down to concave up. And at x equals negative 1, it changes from increasing to decreasing. So there's another one. And at 4, we change from decreasing to increasing. So that's another place. So all of those places, it changes signs, or changes from increasing to decreasing. So you would have x equals negative 5, x equals negative 1, and x equals 4, because f prime of x changes from decreasing to increasing, or increasing to decreasing at those points. Now we can only give the x value for these because, again, that happens a lot because I don't have a function, so I don't have a way, I don't know any values. So that's all I can do. Okay, next thing that we're going to do with the graph is we're going to say, now let's suppose same graph happens to be f double prime. So if this graph is f double prime, we want to know when would f be concave down. So if this graph is f double prime, I've got to quit looking at the shape and I got to say to myself, okay, if this is f double prime, what does f double prime tell me about f? Well, if f double prime is positive, f is concave up. F double prime negative, f is concave down. So they want me to say concave down, so again, from 2 to 6 is going to give me concave down. Again, assuming that the graph of the function is f double prime. So it would be concave down on 2 to 6 because f double prime of x less than 0 there, okay? And then again, it asks me about inflection points. Well, again, if I think about this graph, this is supposed to be f double prime. So the only way to have an inflection point is if f changes concavity. Well, if f double prime, positive or negative, tells me concave up or down, then 2 and 6 will both be inflection points because the graph of f double prime changes from positive to negative and then negative to positive. And so that's what we're going to get for those places. So we're going to have at x equals 2 and 6, and that's going to be it because that's the only place that this function, which is now f double prime, changes. So we're going to have at what values? We're going to have x equals 2 and x equals 6 because f double prime of x changes from positive to negative or negative to positive. So that's how I know I have a point of inflection, is if f double prime changes signs, which it does. Okay, so we're going to skipped that on accident. So we're going to do part D. So now we're saying, suppose this is this graph of this function is f of x. We want to sketch f prime in red, a possible graph of f prime. So again, we look at this graph is f of x, okay? So f of x from -8 to -5 is decreasing, which means its derivative would have to be somewhere underneath the x-axis until we get right here. So it has to be down there somewhere, okay? And then it's going to have to be above the x-axis for when the function's increasing. So it's going to be increasing from -5 all the way to -1. So our graph has to be above the x-axis and hit back down here somewhere. But I also have to think about there's an inflection point right here. So there must be some kind of maximum going on. So this is going to have to go up. And then I got to have some kind of maximum for f prime because there's an inflection point, and then it's going to come back down. And it didn't have to go through that point. That just happens to be how I drew it. And then, because now from -1, if we look from here, now this function, which is called f, is decreasing. So that means my function has to be all underneath. But it also changes from increasing, or from, I got to think about what's happening at like x equals 2. So if we know that this is the graph of f, we're also changing concavity right here. So that means that this graph would have a minimum right here, and then it would go back up until it gets to 4, and then it should equal 0 because of this point right there, right? Because there's a relative minimum. So we have to change, or it's changing from decreasing. And then once it goes past 4, it's got to change to increasing again. And again, somewhere up there, we're going to have a maximum because I have a 0 again, and then back down to 8. Okay? So really look through all of that. We're not going to spend a ton of time on that, so I'm actually not going to do E. Because as long as we can sketch in general or really just tell information about everything, we're good. We don't have to necessarily be able to draw them that carefully. So I'm going to skip that one. So we're going to do number 5, because number 5 says basically if somebody says analyze this graph, okay? So if somebody tells me analyze this graph of this function. So to analyze it, you're going to find things like domain, intercepts, asymptotes, symmetry, normal stuff we did in pre-calc. And then we're also going to find critical points where it's increasing, decreasing, local maximums, concavity, points of inflection, and so on. Okay, so you're going to find all of those things. So for this graph that we don't know what it looks like, that's kind of the point, we want to find the x and the y intercepts. So to find x and y intercepts, so to find x intercepts, they're points, and we're going to set y equal to 0. So if we set y equals to 0, that means we have 0 equals this thing, right? And so if 0 equals that, then we know that our points are -2, 0, and 1, 0. So those are our x-intercepts. Y-intercepts, we set x equal to 0, so that means you're just plugging in 0 here and here. So if I plug in 0 in both places, I'm going to have -2 on this one, and then I'm going to have 0 minus 1, which is -1, but it's squared, so that's a 1, so I'm just going to get -2. So x is 0 and y is or positive 2, sorry. Positive 2. The negative 1 part didn't do anything, okay? Now, find the first and second derivatives. So, you could find the derivatives in a number of different ways, okay? So, you could choose to multiply out what you have up there and get a polynomial, which would certainly be probably the easiest thing to do, or you could do the product rule. I would say I've got to recognize that, hey, the power rule is much easier. So let me multiply this out. So I'm going to kind of use a little scratch area over here. So x minus 1 squared is x squared minus 2x plus 1. And now I need to multiply that times x plus 2. So if I do that, I just have x plus 2 times x squared minus 2x plus 1. And I'm going to write the results down here as what g of x is going to end up being. So you would have x times x squared, so you're going to get x cubed. Okay, then you're going to have an x times a negative 2x, which gives you negative 2x squared, but you're also going to have a 2 times x squared. So those will cancel. And you're going to have an x times a 1, and that's the only, well, I'll have x times 1, and then I'll have a 2 times a negative 2x. So that gives me negative 3x, and then I'm going to have plus 2, because I'm going to take the 2 times the 1. So you take your time and multiply that out, but I would say that would be the easiest thing to do. So now when I do g prime, I'm going to get 3x squared minus 3, which is much easier. And then I'm going to do g double prime of x, which is 6x. Okay, so there's my first and second derivatives. Then it says make a sign chart to find out where we have g of x increasing or decreasing. So that means I actually want to solve when does 3x squared minus 3 equals 0. Factor out of 3, x squared minus 1 equals 0. So you're going to have x equals plus and minus 1. And then obviously x equals 0 for that point for when we do concavity. So to make a sign chart, we're going to have negative 1 to 1, and we have g prime, because this is for increasing, decreasing. So if I go less than negative 1, look right here to plug that in. If I take less than negative 1, like negative 2, I'm going to get 4 minus 1 times a 3, so that's positive. And then if I pick between negative 1 and 1, like pick 0, I'm going to get negative. Pick a number bigger than 1, I'm going to get positive. I don't think too many people have had any difficulties with those, so I'm going to do those sign charts a little quicker now. And then it says to find the intervals where it's increasing, decreasing. So this is g, this is increasing, decreasing, increasing. So we would say increasing on minus infinity to negative 1, union 1 to infinity, and decreasing on negative 1 to 1. And our reason would be it's increasing there. Again, our reason is because f prime of x greater than 0, or g prime, I guess, is the function. G prime of x greater than 0, and here it's decreasing because g prime of x is less than 0. Okay, so those are things that we've done over and over and over again. Okay, determine any relative extrema. Well, because I already have on my chart here, it's pretty simple to see. If I change from increasing to decreasing, I'm going to have a relative max of something at x equals negative 1. So if we go plug that into the original function way at the top, which I've now got stuff written all over where I was doing my distributing. But if I plug in negative 1, I'll have negative 1 plus 2, which is 1. Negative 1 minus 1 is negative 2 squared is 4. So I'm going to end up with a 4 relative max. And then I'll have a relative min. And actually, I'm going to get the same well, I go relative min when I change from decreasing to increasing. So that's going to be at x equals 1. If I plug 1 in back to my original function, 1 plus 2 is 3. 1 minus 1 is 0. So I get a relative min of 0 at x equals 1. Okay? And then my reasons would be because G prime changes from positive to negative and negative to positive, to give you reasons. Okay? E wants me to know a sign chart for G double prime. That one was really easy. Remember, the function was just 6x. So if I'm less than 0, I'm negative, greater than 0, positive. So here we have concave down for G, concave up. Okay? And then, so when I answer my question, again, concave down on minus infinity to 0 because G double prime less than 0. Concave up on 0 to infinity because G double prime greater than 0, okay? Identify any points of inflection. Well, did it change from concave down to concave up? Yes. So point of inflection of blank, so 0 comma something. So I got to go up to the original function and plug in 0, and I'm going to get 2 times 1, which is 2. So I have a point of inflection at 0, 2. And the reason it's a point of inflection is because G double prime changes from negative to positive. Or you could say G changes from concave down to concave up. Okay, then it says sketch it. Okay, so we're going to go back, given all this information, which you should have all written. Oh, need to get to my graph page. You should have all that information written. So you just have to think about that. Now this time I have points, right? So, because we know things that happen. So I would plot all those points and then aim towards them. So we have x-intercepts at -2, 0, and 1, 0. We have a y-intercept at 0, 2. So those are points that we know. We have the function relative max of 4 at x equals -1. So that's going to be a relative max. And then we have a relative min of 0 at x equals 1, which is already written on here. So that's going to be a minimum. We know it's concave down from negative infinity to 0, but it is increasing from negative infinity to -1. So that means it's increasing here and concave down. And then it switches to decreasing, but it's still concave down until I get all the way, or just right there to 2. And then it changes from concave up from 0 to infinity, decreasing until we get to 1, and then increasing past that. Okay, so there's my graph. Okay, so we just use all the information. You may need to take a little bit more time and think through that a little bit in order to answer that, okay? But go back, that's the nice thing about video, go back, watch it again, change some things around. So I'm going to skip example 6, we're going to do example 7. So here we have this graph, and it's consisting of segments and semicircles that are listed. This graph will be really important later when we do integration, because we're going to actually do some other things with it, but right now this works, we're just answering things for this chapter type stuff. So first question is, find the x coordinate of each critical point. So we go back, and this is important. This graph is f prime. So again, sometimes you might think, you might want to write derivative real big, because then that tells you, hey, this is the derivative. This graph is. So the question is, find the x coordinates of the critical points, okay? So critical points would be where the first derivative equals 0 And that's going to be at -4, 0, and 6. That's where the first derivative equals 0, or would be undefined, which we don't have that. So critical points occur at -4, 0, and 6. Okay, so these are critical points. This is when the first derivative equals 0. We're only supposed to answer the values that are in between in the open interval, so we're not going to count 6. So 6 is not going to be a critical point, which makes sense, right, because it's an endpoint, so you can't change from positive to negative or vice versa on an endpoint because there's not another side. Okay, then it says find the x-coordinate for each relative extrema and decide if they're max or mins. So again, if these two places, so we won't count that one, if this and this are your critical points, and this is f prime, it's going from negative to positive here and positive to positive there. So you're not going to have any kind of relative extrema anywhere except for at -4, and it changes from negative to positive. So you're going to have a relative min at x equals -4 because f prime changes from negative to positive. Okay? Find the open intervals where f of x is increasing. Okay? So if f of x is increasing, then this derivative would be above the x-axis. So that means it is increasing from -4 to 0 and then 0 to 6. Now remember, it's not above the x-axis at 0, so that's just a safer thing to just not answer that, okay? So we want to say it is increasing on -4 to 0, union 0 to 6, and then decreasing then, if we look back at the graph, it is going to be decreasing from -6 to -4. That's the only place that f prime is below 0. And this is going to be where f prime is greater than 0. And this is going to be decreasing on -6 to -4, where f prime is less than 0. Okay? So there's our definitions, and there's our increasing, decreasing. D says find the coordinates of each point of inflection. So this is the derivative. So you're going to have a point of inflection if this graph changes from increasing to decreasing or decreasing to increasing. Okay? Because this is f prime. So at 4, certainly, f prime changes from increasing to decreasing. Okay, so there's a point of inflection. At -2, you also change from increasing to decreasing. So both of those would be points of inflection because f prime, double prime changes from positive to negative, or f prime changes from increasing to decreasing on both of those cases. At 0, f prime changes from decreasing to increasing. So that's also going to be a point of inflection. And that's because, again, f double prime changes from negative to positive. Okay, so let's answer those. So x coordinates of each point of inflection we have at 4 and -2. Because f prime changes from increasing to decreasing. So that's a point of inflection. And we have at x equals 0 because f double prime, or f prime, changes from decreasing to increasing. So those would all be points of inflection. Okay, find where the function is concave up or concave down. Well, we literally sort of figured out where the points of inflection are. So you're going to go from -6 to -2, union 0 to 4, to be f is concave up, because that's where the function was going from increasing, or is increasing. So if we look, we have from -6 to -2, this function is increasing all this way. This function is increasing. And then from 0 to 4, of course, we have this segment there. It's increasing, so it's decreasing on the other parts, which means that it is concave down. So from -2 to 0, union 4 to 6, f is concave down. And your reason is concave up because f double prime greater than 0, f double prime of x less than 0. Okay, so those are your reasons. Okay, so that was quick on that one. So again, go back and sort of look over that for a second and think about it. So the last example we're going to do for the video is going to be example 8. So on this example, we're going to look at a table that gives us a bunch of stuff that's true about h, h prime, and h double prime. And then we're going to use this table to sketch what's going on for our function. Okay? So I want to look through and kind of just make some notes in this table, and then we'll graph it. So when x equals 0, we know that h of x is 3. So we'll be able to actually put a point there. Then from 0 to 1, we know that h of x stays positive, which just tells me I can't, and then I get to 2, I get 0. So that means I'm going to stay above the x-axis until I get to 2, and then I'm going to hit 0. H prime is negative from 0 to 1, which means that my function is decreasing from 0 to 1. At 2, it's also negative. It's -3, so I'm still going to be decreasing. And then from 1 to 2, negative again. So I'm going to keep decreasing from basically 0 to 2. And then at 3, I suddenly have a first derivative that does not exist. But at 3, I definitely have a point here for h of x, which means that I have to have a cusp or something going on there. So let's figure it out. So from 0 to 1, f double prime, h double prime is negative, which means I'm concave down. At 2, it becomes 0, which means now that's a point of inflection because from 1 to 2, it's positive. So here we're concave down, here we're concave up. Okay, and then we know here we're going to be decreasing, decreasing. Okay, so we're going to be decreasing and concave up to run into at x equals 3. Okay, then from 3 to 4, we change, and now we're going to be below the x-axis. We've already been below the x-axis actually here, but the derivative is positive, which means we're going to be increasing and then increasing. Okay, and we know that the second derivative is negative, which means I'm concave down, and then positive, which means I'm concave up. Okay, so somewhere that changes. Okay, so you have that table in front of you, so let's look at all the things that means. So we know that we have a point at 0, 3, because that's given in the table. We know that we have a point at 2, 0. We know that at 3 we have -3, and we know that at 5 we have 0. Those are points right in the table. Okay, and then we know from 0 to 2, oh, and I guess there's a mistake on this thing. Yours may be right. That's supposed to be a 2 there. I thought that was a little weird. And then this should be 2 to 3. So I don't know if that's what yours says or not, but that's what it should say. So it may just be on this power or this slide that it's wrong, but that's what it should say. So we go from 0 to 2, we know that we are decreasing and concave down. So decreasing and concave down. Then when we get to 2, we know that we change and we're still decreasing, but we're now concave up. So that's concave up to here. Then when we get to 3, we know the derivative is undefined, which is why we have this thing going on here. Let me draw that a little better. There we go. And then from 3 to 4, we're supposed to be increasing but concave down until we get to 5. So we're increasing but we're concave down. And then at 5, we change to concave up and still increasing. So we just do this. Okay? So good questions to look over some more and really think about. These are really good questions to help you get that connection between your concavity, your first derivative, second derivative, and so on. So if you need to, go back and look through some of these again, pause it obviously at any time and go back and think through it. So that's the end of our curve sketching video.